I think we're at the top of the hour. Let me just say hi to everyone. Thank you for joining us today. My name is Vicky. I'm the product manager of MSC Nastran, I'm here really excited today to talk to you about MSC Nastran PEM, or Poroelastic materials for trim components in MSC Nastran. Now, for those of you who are not as familiar with the topic, do not worry. We'll be covering both theory and the practical side. So I'm just going to walk you through the core theory behind how MSC Nastran handles poroelastic materials and the applications and how it fits into the broader NVH simulation schema. And then I'll hand it over to Grigoris Kalaboukas from our partners at MSC Systems, who's here today with us, and he's going to walk us through a live demo on how to do the full setup for MSC Nastran PEM in ANSA and Meta, showing you everything from pre-processing to post-processing and how to set up your MSC Nastran solver deck. So whether you're new to this or already working with NVH, I think you'll get a lot of valuable insight from today's session, so stay tuned. Let's start a little bit by discussing the importance of vehicle compartment noise and its impact on the overall experience of a vehicle. In today's automotive industry specifically, the noise levels within a vehicle's cabin are a significant factor in how customers actually perceive the quality and the comfort of their vehicles. The trim components, as they are actually described, include parts like carpets, insulation, interior panels, and so on, and really play a pivotal role in enhancing the overall cabin noise performance. Now, trim components are not just simple layers, as many people think, but they are rather sophisticated structures which are made up of porous materials, viscoelastic elements, and air layers sometimes. So these components work together to provide complex damping, absorption, and insulation effects, all of which contribute to the reduction of the noise within the interior cabin. And let's see on that on this slide over here. So just to give you a quick idea of what the operating mechanisms are for the acoustic streams, you can see over here on this slide, we will look at the mechanisms of insulation, damping, and absorption. So talking about insulation and damping first, when a vehicle structures vibrate, as you see over here, it transfers energy to the trim components. A portion of this vibrational energy is dissipated within the trim itself, contributing to what is called the damping effect. And this damping effect not only reduces the vibrations of the structural panel, but also plays a crucial role in lowering the noise radiated into the cabin or the air cavity that you see over here. So essentially, you can think of the trim acting as an insulating barrier, which helps to keep the unwanted noise out of the passenger compartment. Now, we also have absorption that you see over here. So as the pressure waves hit the trim components, part of the energy from these pressure waves is absorbed within the trim, while some of it may be transmitted to the vehicle structure, and the remaining of the energy is reflected back. So this is a basic idea of how the trims operate and what their mechanisms are. Now, if we have to look how we take those into account in MSC Nastran, you can see, I would say, the basic workflow over here. Okay, before I do that, let me just give you a little bit of background on what the impedance matrices are, because this is very, very important from what we're going to discuss later on in this presentation. So in the context of structural and fluid dynamics, the impedance matrices represent the relationship between forces applied to a system and the resulting velocities or displacement. So they essentially capture how the system resists motion, whether it's structural component or a fluid, across various degrees of freedom. So this matrix becomes particularly important when we're analyzing systems where different domains like fluid and structure interact with each other, such as in the case of fully trimmed bodies. So To streamline this process, we usually begin by identifying candidates for the reduced grids, key points where the interactions are most significant. And after we identify those points, the impedance matrix is reduced in the physical coordinates, which simplifies the system, okay? And we still capture the essential dynamics of the system as well. And then what we do is we take the reduced impedance matrices, or RIMS as an abbreviation, something I'm going to use in this presentation moving forward, and we project them onto the fluid and the structural model basis. So this projection over here, what it does, it just allows us to integrate the effect of the trim components into the broader dynamic analysis that we have, aligning, of course, with the dominant modes of vibration for both fluid and structure. Okay, so we add the trim contribution to the dynamic behavior of the coupled problem in a way that maintains both accuracy and computational efficiency, and of course in a way that is actually going to yield more accurate results for any dynamic analysis that we are actually doing. Now, what's important over here is that is the powerful handshake that this workflow entails. So it's Nastran coupled with Actran, our powerful acoustics solver here at Hexagon, which basically Actran computes the impedance matrices and gives them, seamlessly hands them back into Nastran. Okay, it's a very easy to learn solution for Nastran users. It stayed within the Nastran user experience, and it's an integrated, fully integrated solution. So this is how basically I would say the PEM workflow works for Nastran and Actran, of course. So covering how the we just covered how the current PEM workflow functions in MSC Nastran, and I would like to show you a little bit how things are done currently. We're dealing with non-model trim components, so or in the past, because many of the organizations are actually using MSC Nastran PEM approach. So what usually was done is we would often approximate the damping and absorption effects using methods like the non-structural mass and concentrated cone-M2 techniques that we're all familiar with. And to further account for these effects, it's also very common to apply high levels of cavity fluid damping, typically in the range of 5 to 8%, as you see over here on this slide. But as we move, and here as an organization, as we move to the more accurate PEM approach, we need to remove or deactivate those old modeling elements or techniques. So, of course, PEM, as I just mentioned, provides a much more precise way to represent those components. So we no longer need to rely on those approximations that were done in the past. So just to give you an example over here, instead of relying to large damping values and applying those for the system, what we recommend now is to use a constant critical damping value of 0.5% for the cavity fluid across the frequency range. And here you can see the several ways that you can achieve that in MSC Nastran. So there are 3 different ways. I'm not gonna go through all of them, just to give some time to Grigoris to present his demo as well. Now, moving on to trim modeling, I would like to describe this very, very powerful technique that it's available in MSC Nastran today and offers a great deal of flexibility, which is the 1D analytical trim. Of course, you can still choose to completely mesh the trim components if you want to, but I'm sure that, and Grigoris, I'm sure he's going to walk you through that as well during his demo. But what's really exciting about the 1D analytical trim is that you don't have to mesh the trim necessarily. So you can use the 1D analytical trim approach, which simplifies the entire process and drastically, of course, reduces setup time. And it's particularly useful when you're doing concept studies, you want to do something quick and dirty, and you just want to take into account the trims. This is actually the solution. So if you were to see what exactly are the 1D trims, essentially we're talking about an analytical method for modeling the layered trim components, which uses the transfer and admittance method. So instead of relying on the usual finite element mesh that we have for the trims, we eliminate the need to mesh those layers all together. So as you can imagine, this really simplifies things. So By removing the need for those anterior 3D meshes, we can significantly reduce the model size, of course, which in turn means faster setup and faster computational times. Every time you make a design change, like for example, adjusting the material or the thickness of the layers, you can update the trim properties directly, which saves, of course, a lot of time, particularly when you're optimizing different vehicle configurations. And another big advantage, before I conclude with this slide, is that this approach is very, very well suited for high frequency simulations, because since it's an analytical method, you can work efficiently at the higher frequencies, whereas sometimes traditional 3D meshing would be very, very computationally intensive for that. Moving on to the trim coupling with structure and cavity. As you see over here on this slide, there are two primary techniques to perform the trim coupling. One is called the taped over, and the other one is called wedged in. And I'm going to walk through both just now. The first one, the taped over, means that the trim component can overlap portion of the structure, as you see over here, and of course the fluid model. On the other hand, wedged in means that the trim component is placed directly in between the structure and the fluid model. So with the taped over technique, the trim model can encroach, as you see over here, both the structure and the cavity space, and the coupling between the trim, structure, and cavity is handled by the algorithm's tolerances. What the advantages of those approach are is that it preserves the initial cavity shape, and it allows you to add the trim treatment, ensuring that the cavity's acoustic properties remain intact. And it's extremely useful for adding trims to the existing fluid structure interaction models that we might sometimes have, where modifying the cavity or the structure might be extremely challenging. Additionally, this method is very effective when the trim's thickness is much smaller than the cavity dimension, which makes it a very practical and handy choice for thin trim layers. Now, on the other hand, the wedged in approach that we just saw provides a real gap between the cavity trim and the structure trim. And this method is really recommended when the trim's thickness is on the same order of magnitude as the cavity dimension. The wedged in technique that you see over here is actually designed to accommodate thicker trims much more accurately. Now, one important consideration when using this technique is that if there's significant separation between the structure and the fluid, the tolerances that you have on the AC model card of MSC Nastran might need to be increased, particularly if the trim is removed during the analysis. So this is going to ensure actually that the coupling remains accurate and reliable. Overall, the wedged in strategy is what we suggest as a first choice when we aim for optimal and accurate results. Now, let's delve into the actual interface coupling condition and constraints when we're dealing with trim components in contact with an acoustic cavity. We classify those conditions into three main types. We have open, impervious, glued, along with specific cases like sliding and air gap. Starting with the open condition, as you see over here, we have this when the trim layer in contact with the cavity is considered to have open pores, and air can flow freely through the interface between the fluid phase of the trim component and the acoustic cavity. What this scenario is particularly useful for is because it allows the acoustic energy transfer across the interface, which affects the overall acoustic performance, of course. With the previous condition, this happens when the trim layer has closed pores. On the other hand, so the airflow is blocked at the interface between the fluid phase of the trim component and the acoustic cavity, which results in no acoustic energy transfer. And this setup is usually used when we want to isolate certain acoustic characteristics. Moving on to the glued condition, this ensures continuity of the displacement field at the interface, which results in a complete structural coupling along the X, Y, and Z axis, as you see over here. And this is typically used for parts that are screwed or glued or they're really clamped together, and the reduction models carry the all three degrees of freedom related to displacements. For the sliding condition, on the other hand, we maintain the continuity of the normal displacement field at the interface, but it allows for in-plane displacement discontinuity. Hence, we use the term sliding over here. This condition is used for layers just in contact with each other or lying loose on the structure, like, for example, a heavy carpet. And the reduction node carries only 1 degree of freedom, which is the normal displacement. And lastly, we have the air gap condition, which is used when we have very thin air layer between the trim component and the structure without being physically modeled. And this setup requires biphase elements attached to the trim coupling interface. The reduction nodes over here carry 2 degrees of freedom, normal displacement, and pressure as well. All these boundary conditions that we just described can be combined within a model, and that's very important to note, because we might think of trims that serve different conditions over here, and we want to model those in our analysis. So, for example, as you see over here in a vehicle cabin model, typically 90% of the floor trim lies on the structure, corresponding to a sliding air gap condition, while the remaining 10% is glued to the structure to hold the trim in place. It's also very important to consider how the type of connection impacts the storage requirements for the reduced impedance matrices that we just discussed about. It's not just something that you model, but you have to take into account how that will impact your analysis and your solver later on. So in the sliding conditions, as we just discussed, only 1 degree of freedom per wetted grid is activated, whereas in the glued condition, we have 3 degrees of freedom per wetted grid that are activated. So this difference in activation can have significant implication on storage computational times. So, for example, switching 100% of the trim surface from glued to sliding can lead to a substantial reduction in the reduced impedance matrix size, because the rim is stored in the physical coordinates, just to give you an example over here. How to accelerate the run, it's all about that on this slide. So the PEM capability within the solver performs linear interpolation for the reduced impedance matrices of each trim component. And on this slide, you can see actually how this works. The computation of the rim is performed on a subset of the driving frequencies, which are specifically selected based on the characteristics of the trim components in the frequency range of interest. And once those rims are computed, the solver will interpolate between the values stored in the trim database to estimate the rims for other frequencies that were not explicitly calculated. So linear interpolation is used for frequencies where the rims were not directly computed, and that is going to fill in the gaps between the known data points. And in order to enhance accuracy, it's recommended to use a combination of logarithmic plus linear interpolation steps across the frequency range. Specifically below 100 Hertz, it's advisable to use logarithmic interpolation, as you see over here on this slide. You can follow these guidelines, which is going to end up approximately with a set of about 20 rim interpolation points, with 10 points derived from logarithmic interpolation for low frequencies and another 10 from linear interpolation for mid and high frequencies, covering the range up to 500 Hertz. And this is going to ensure that the rims are accurately represented across the frequency spectrum, which of course in turn is going to result in more precise simulation results. Now, let's explore the concept of trim partitioning, which is very, very important for any MSC Nastran PEM analysis. This approach is specifically used in order to manage computational resources when we're working with large trim components in a simulation. Trim partitioning becomes necessary when the required RAM is insufficient to solve the trim database sequence. And we have this key control parameter over here, param PEM and part X. X is the number of partitions that you are going to use. and it governs basically the number of partitions for one given specific given trim component. What this process does basically, it divides the trim component into equal parts, considering the number of nodes and elements as well as the size of the trim file, in order to generate the shortest possible interface between all the trim parts to optimize the partitioning process. It doesn't take into account any potential symmetry that might be there in the model. And it's extremely useful when we're dealing with non-connected parts, seats within the trim component. We don't recommend, or I would say, we use trim partitioning sparingly, as increasing the number of partitions might actually result of more significant loss in accuracy. But splitting trim elements into multiple sub-trim partitions will help reduce the peak storage requirement for the rims, leading to, of course, a reduction in computational demands without compromising accuracy. We have a number of best practices that we can share with you. They're also documented nicely in our users guides and so on how to use this feature effectively to achieve, I would say, the best trade-off between accuracy and, of course, computational times. On this slide, you can see the key properties of porous materials. We have porosity, we have tortuosity, the viscous characteristic length, or the thermal characteristic length, and so on. While I won't go into much detail on what each of those, I would say, properties are, I would like you to keep in mind that when performing an PEM analysis, these material properties are essential in order to do the analysis. So we need to have those properties available in order to proceed with the MSC Nastran PEM calculation. Before I wrap up today's session, I have two more topics. One is the perforated cells, and one is the, I would say, HPC aspect of HPC, and then I'll pass it on to Grigori. So, why I selected this perforated cell features, just to show you one of the neat features that the MSC Nastran PEM has, which showcases the extensive functionality and capabilities of the solver. What is perforated cell? This feature basically allows you to model perforated cells, which are very, very common, as we know, in many acoustic systems, like, for example, your exhaust muffler and so on, without having to mesh the fine holes individually. So the meshing effort is completely eliminated. You don't have to do any detailed meshes and so on in order to account for this effect. It's taken directly into account within this functionality of MSC Nastran PEM, which is called perforated cell, and you can see over here the respective keywords. So, talking about that, I'm going to move on to how we can optimize the computational times for PEM calculations, and then I'll pass it over for the live demo. So, you see over here the PEM DMP parameter highlighted. What's that? Essentially, this parameter, what it allows you to do is to distribute parts of the computation across multiple machines. That's what it stands for, distributed memory parallel, which is significantly going to improve efficiency. The way it works is basically splits the entire frequency domain into several ranges, and each one of those ranges goes to a different machine. It gets treated, think of it, it gets treated as an individual job, which can be processed in parallel. So, in order to have, I would say, a more efficient, a faster MSC Nastran PEM analysis, ensure that you're using the distributed memory parallel while you submit your run. I know many of us submit the runs to clusters and so on, so make sure that the DMP parameter is activated when submitting there. What you need to do is simple. You just need to set PEM DMP yes to enable this feature, and of course set a DMP number which is greater than 1, meaning that you need to have more than 1 DMP nodes available in your system. Use, of course, ACMS, and we need to have at least one PEM trim component present in the model. The benefits are obvious: computational time reduction for any MSC Nastran PEM run, without, and one important point here is with or without panel participation factor. So you're going to have a dramatic reduction in your computational times to have more efficient simulations. And before I conclude today's presentation, again, it has to do with performance. We introduced this feature in 2024.1. This is a brand new method to compress the reduced impedance matrices in the model approach. We discussed how important the rims are for this type of simulation. And in 2024.1, we took it a step further by actually compressing the rims in order to decrease both computational times, but also storage requirements. Whatever I/O is happening there, and as well as the storage requirements that are needed for MSC Nastran PEM calculations, which were pretty intensive actually in the past. So with this approach, you're gonna see tremendous benefit, and something to say without compromising on accuracy. This is well documented in 2024.1 release. You can watch the videos and so on, and feel free to reach out to us if you have any questions. In terms of results, this is exactly the difference that you see with a bare configuration over a trim configuration, right? And you can see over here that when we're talking about MSC Nastran PEM really influencing the accuracy of the results and giving you much more accurate results, this is exactly what we are talking about. And if you see, for example, in the range of 100 to 200 hertz, you can see over here that the trim configuration offers substantial benefit for our NVH analysis and so on. So without further ado, Grigoris, if you want to take over, show your screen and walk us through this this example.
Okay, thank you very much. So this is Grigoris Kalaboukas from Beta CAE department. First of all, thank you, Vicky, for this detailed presentation. And now we'll continue, and we'll go through a small slideshow regarding ANSA and meta capabilities regarding the vibroacoustic analysis with Poroelastic trim components. And then we'll continue with a live demo within ANSA and Meta, our softwares, in order to show to you all the capabilities that we provide. To begin with, regarding the modeling within ANSA, it is mandatory to have 3 includes as your in order to do the modeling. One will be the structural part, the second will be the fluid part, and the third one will be the trim part in your ANSA database. Regarding the ANSA setup, it is very easy to set up all the needed Poroelastic material keywords. And actually, 2 keywords are needed. The one is the ACPMCP keyword, which defines the interface coupling conditions and constraints of a trim component. And the second one is the PRMCPL, which actually defines the interface coupling parameters for computing the interface coupling matrices. Regarding the Nastran header in the output, in the executive control command, it is mandatory to include a DMAP, an output file that we have created in collaboration with MSC, and we are going to share this file with you. And this is mandatory in order to output the OP2 file, to output the modal matrices, the PEM matrices inside the OP2 file. Apart from that, in the case control command, it is mandatory to create 2 subcases. So the third subcase will be the one that I'm showing here in the screenshot, which it will be with analysis equals modes in order to calculate the solution 103 results and output all the results inside an OP2 file. And also the trim GRP keyword is needed, which actually it is creating, it will select the set of the trim components for your analysis. And finally, in the bulk data section, these params are needed. The first one is the param post -1 or -2. It depends on if you want to output the results in global or in basic coordinate system. I think you are all familiar with this. Param post text, yes, this it is needed in order to output the full matrices in the OP2 file, and also the param TRM BIM model, which this parameter is used to define the formulation used for the reduced impedance matrices, with abbreviation RIM, for all the trim components that you have requested under the trim GRP case control command. Its default is physical. The default value is physical, which it will generate the RIM in physical coordinates. But in order to output the modal matrices in the PEM matrices in the OP2 file, it is mandatory to switch this parameter to modal in order later for our software to be able to read all the PEM matrices and do the post-processing calculations. Afterwards, in Meta, we have a tool, the modal response tool, which the modal response tool is a mode superposition tool. And by using this tool, the user has just to provide the modal basis of the structure, and the tool is able to perform the modal frequency solution 111 analysis very easily by setting up the loads, the frequency ranges, and the responses. When running the analysis by using all the previously parameters that I mentioned, inside the matrices, there will be the PEM matrix that Meta is able to read, and by including or excluding this checkbox, it is very easily to do some what-if analysis for your models. And as you can see, the Nastran results and the Meta results by using either the trim configuration or the belt configuration are line on line by using our modal response tool. Let's proceed. I will start now the live demo. This will be my model, and my starting point. For the starting point, I have already loaded the structural part, the fluid part, and the trim part. I have already created a solution 111. So as you can see here, I have already defined the D area. The D area is just a keyword in order to define the factor for static and dynamic loads. And for the dynamic analysis, the D area is used along with the R load entities. So in our database browser, the R load is already set up. Here, I will just apply a unit load in the specific node in the Z direction. Also, just a small introduction regarding the header that it is already set. I have already defined the ACMO DL card. This card is needed in order to define all the modeling parameters for the fluid structure interface. And also, I have already created a set for the nodes that I will request the response. So I have requested responses, one for the tactile response and one for the cavity response. More info regarding the database browser. I have already two frequency cards. One, it will be for the full model, where I will define it from 10 to 200 Hertz. And the second one will be the interpolated frequency in order what Vicky explained previously, in order also to that this will be addressed for the trim component, that Vicky explained to you that it will also reduce the total computational time. So let's proceed. I'm ready to start to creating the PEM. What is needed for the PEM. So in the Nastran tab here, in the Nastran deck, under the auxiliaries tab, there is a button that is called PEM. When the user presses this, there are two keywords, the ACP MCP and the TRM CPL, as I had mentioned previously in my presentation. The first one that it is needed is that the user has to select the ACP MCP keyword card in order to define the interface coupling condition and constraints of a trim component. The first two entities, the exclude and the SS slide, they address the sets of grids that they belong to the solid phase of the trim component. The first one is those if you want to have them as glued to the structure, and the second one is if they are sliding to the structure. And by pressing the question mark in these cards, the user can very easily select the sets that these grids that they will belong to the solid phase trim component. In my case, I will add them as slide. So by pressing the question mark in this card, all the available sets that I have, they are coming into display. As I mentioned, the first two are for the structural phase. So I'm selecting the structural the set with ID 32 and the S open and S imper cards. These are the identification numbers for grids that they belong to the fluid phase elements of the trim components. The S open is that for those that they have an open interface with the cavities, and the second one is if these grids have an impervious interface with the cavities. I will, by pressing the question mark, again, I will select now the fluid phase. The definition of this card has been finalized, so I'm pressing OK, and as you can see here in the under the FE auxiliaries in the database browser, under the PEM tab, the card that I already created has been filled here. The next step is that for the, again, under the PEM button, I will have to select the TRM CPL card. The TRM CPL is in order to define the interface coupling parameters for computing the interface coupling matrices. So under the C-type card, I will select the S slide, which it will address here the parameters for the structural phase, and by giving here some threshold values regarding the tolerances, I will be able to fill also this card. I will use the default values. The PL12, for example, is the relative tolerance for the in-plane acceptance with respect to the C-type, to the S slide. So I will use the default value 0.1, and for the second one, the gap 1, it's a card which defines the absolute tolerance for extrusion with respect to C-type. And again, I'm going to select the default value, which is 0.01. Since I do this for the structural phase, I have to do the same for the fluid phase. I press OK, and then I will create a new TRM CPL card. And in this case, in the C-type, I will select the S imper for the fluid phase, and by giving again the same values in the PL12 card and in the GAP1 card. I will put here just 0.1 and 0.01. With this way, I have created for the PEM component that I had. Let me show to you also my as a standalone the PEM component, I have created all the needed cards and parameters for this component. Of course, if I have more trim components, I can proceed with the same way to create these cards and to define the interface coupling conditions, constraints, and parameters for the rest of the components that I have in my analysis. Let me close this. And the next step is to switch to the Nastran header and then to adding all the parameters and in the executive command, in the case control command, and in the begin bulk section that are needed in order for Nastran to run and to create the results in order for them to be later to be used with Meta. Here, as I had mentioned, I have already a solution 111 header file, which I have the methods, the frequency request, and the responses and the deload. The first step is under the solution 111 to include this dmap, this alter file that we can provide for you that you are because it is needed for the analysis. So I'll just have to include this. I'll type this as include. I'll just give the name that this file has. And actually, I can also show you this file. I'm going to show this to you later. Okay. The second step, I have set up the dmap that it is needed is to select the set of the trim component. So by using the keyword trim grp, here the user can either select as a set of the trim component for his analysis, or he can use all. If he has more components, he can select all of them, whatever he wants to do. Again, by pressing question mark, I will select the ID of the trim component, and you can see here that the set has been filled in the Nastran header editor. Third step is to create the two subcases step in order for my solution 111 to output the results that I have requested, the responses, but also to output the solution 103 results during the solution, but they will include also the PEM matrices that I would like to have available in the result file. So I can just here build it by creating two subcases header. The subcase 1, it will have a label equals, let's say, modes, and the analysis type I'm going to select from this drop-down menu. Again, it will be analysis modes, and I will request to have displacement results for all the grids that I have in my model. So very easily, by selecting the displacement, here we have the all these functionalities that they are helping the user to autocomplete what it is needed. So in my case, I will select plot, and here I will select also all. I press this button, so all the available results for all the grids will be output in the OP2 file. And again, later I'm going to fill this for the subcase 2, where the subcase 2 will correspond to the 111 solution that I have already defined. And finally, in the bulk data card, the user has to add on his own 3 more params in order for the MSC to calculate the M matrices and then Meta to be able to read them. I'm going to use the param post text yes in order to output the full matrices. Specifically for the M, it is needed the PRM DIM model in order to produce the rim in modal coordinates, and of course param post, for example, -1 or -2 if you want to output the results in global or in basic coordinate system. I have finished with my my setup, so very easily you can output this file that you have built, and by running it with ACMS in order to take all the computational benefits that Vicky mentioned, you can create the results for your analysis. Let's proceed with Meta and view how we can evaluate these results and what post-processing capabilities we have. I have already loaded the geometry, and I'm going to switch to the modal response tool, which is the mode superposition tool, and I'm going to provide the modal basis of the structure that MSC has calculated. So in this tab, under the modes tab, the user has to select the OP2 file, and by pressing enter, in this field, all the modes and their related frequencies, they will be come into view. In the info window, let me expand this a little bit. In such cases that you have output and you have requested to output the modal matrices and for the PEM matrices, the user is informed that the modal viscous damping and the modal stiffness matrices were found in the modes file, and specifically also that the modal matrices for one PEM component has been found in the modes file. This, the user can also view them if he switches to the matrices in this matrices tab. So all the matrices, all the information for the matrices is being stored in this window. The next step for the user is to switch to the frequency response, and with this interface, the user can set up the loads, the frequency ranges, and the response for his analysis. I'm going to create the same load that I created with MSC Nastran. So I will just add a load in node 6390 in the Z direction. I will set up the frequency range as I had my interpolated one from 10 to 200 Hertz. And also for the responses tab, I will request to calculate the response for my pressure node, which it was the node 3606. I select this, so you can see that Meta automatically identified that this was a pressure node, and the tool now is ready to do the calculation by pressing the calculate button. I will leave this as it is because it's the default definition. So by default, when all these matrices exist, Meta is taking them into consideration for the calculation. And I'm going to press calculate in order to calculate the FRF results. So you can see now that I have calculated for the specific frequency range from 10 to 200 Hertz, the pressure result for the specific node. Let me change this to dBA, for example. And by switching back to matrices, then here it is possible to make some what-if studies, how the response will be affected if I enable or if I disable the PEM a component. Very easily, I can deselect this PEM, I switch to the frequency response, and I can press calculate. So when I press calculate, you can see the new response here by ignoring the PEM configuration that I already have. And in order to do also a correlation, I have already run for the solution 111 by using MSC. So I will select the trim configuration and the bare configuration. I will select from this drop-down menu again to read the acoustic results for the specific nodes, and I will plot them in the same window. I press read, and if I switch to the plot list, I can see that the results for the, not this, it's this. The results for the trim configuration are line on line, either directly reading them from the PCH file from solution 111 of Nastran, either for the trim configuration or for the bare configuration. So by using this tool, since you have all the modes available and for the results for all the grids, it is very easily just to switch and to do what if analysis by selecting different nodes, different kind of responses, and by enabling or disabling the PEM option from the matrices tab to view what is the difference in the response if you take the PEM component into consideration or not. So thank you very much. This was the presentation from my side and the demo regarding ANSA and meta capabilities.
Yeah, just to give some context as well for the rest of the audience here. They asked us before if there's any limit for how many machines can be used for the parallelization of the PEM. We said it's not recommended to use more machines than the number of trim parts that we're trying to solve. Now, another question is, what was the highest dimension of the matrix you tried to solve? This one goes to Grigoris, because the model that we used actually is not that big. It doesn't have that many trim components. It's real, I would say, real world use cases, but we've seen from our automotive customers extremely large models being solved that, of course, increase the size of the matrices as well. And that becomes very efficient for the solver. Yeah.
We do not have any limitation in meta. We can read as many matrices as the model has. No limitation at all.
Yeah. All right. All right. One more question that we can just before we finish this is, what's the calculation time benefits if we're using analytical trims? As we said, the analytical trims allow for quick modeling. They become particularly useful for concept studies. So you actually basically avoid all the time you would need for the meshing, right? And you can still check how your model would behave, in the presence of the trims without having to use the coarse approach of modeling them with Column 2 and NSMs and so on. Okay. As far as poroelastic materials, and that will be the last question, as I said, for the definition of the poroelastic materials, there are several parameters that you need to set up. And those parameters usually usually come they usually come from your organization. So you need to ask someone to provide those. It can be via labs that do the experiments and so on, and provide those material properties for you. And finally, the 1D trims are not available only for 2024.1. No, they're available from before. The only thing that we introduced in 2024.1 is the compression of the reduced impedance matrices, which results in faster computational times. The 1D trims have been in MSC Nastran for a while now. Does the PEM give us reliable results on high frequency? Yes, absolutely. That's a resounding yes. Yes, and we also recommend to use that with ACMS, of course, and MAMS as well, to speed up computational times. Yeah. Okay, so that's all for now. For any other questions, we'll reach out to you independently. Thank you for attending today's session. Melinda, back to you.
Thank you very much, everyone.